Hello, so today we're going to do sampling distribution of the sample mean. This is one of the important topics to understand the link between probability theory and statistics, so between theory and practice. Okay, so let's get started. First, I will start reviewing Central Limit Theorem from probability. So Central Limit Theorem states that if you have n random variables that are independent and identically distributed, so IID, with mean mu and variance sigma squared, if you consider a new random variable xn bar, which is the average of the n random variables, then as n gets large, your xn is roughly normal, or in other words, xn bar minus mu divided by sigma over square root of n approaches to z distribution. What is z? Z is the standard normal with mean 0 and variance 1. So in other words, you often start with any distribution. It could be right skewed, left skewed, it could be normal, it could be different distribution. But regardless of whatever you start, the Central Limit Theorem states that when you take the averages with sample size increasing, your distribution x bar will become a bell curve, will be roughly normal distribution. So there are three things that we need to take away from Central Limit Theorem. First one is that xn bar is roughly normal when n is large. Secondly, the expectation of xn bar is mu, and variance of xn bar is sigma squared divided by n. You see, variance is getting smaller, right? Because you're divided by n. That's the crucial part. Now, let's demonstrate why the expected value is equal to mu. So what is the mu? Mu is the expected value of xi. Well, so using the properties of expected value, xn bar, what is this? This is just the sum of, so we know that the expected value of sum is sum of the expected values, right? So here it's x1 through xn, expected values, and then I divide by n. Each one is mu, right, mean, so it's mu plus mu n times divided by n, so this is simply mu, right? So that's the first one. Okay, how about the second one? Well, for the second one, we have the similar property for variance, but we need independence, and indeed we have the independence. So variance of xn bar, okay, so this is I can write it this x1 divided by n, x plus x2 divided by n, so on and so forth. Then it becomes the variance of x1 divided by n through variance xn divided by n. Now from properties of variance, we know that this is variance of x1 is sigma squared. Here it comes out as n squared. Okay, so there are n of such terms. So this becomes like n times the sigma square divided by n square. So cancelling one of the n's with the denominator, you get sigma square divided by n. So that's the variance part. Okay, so you need to remember these three conclusions from Central Limit Theorem. Now, before giving the learning objectives, let me start with a problem statement. Let's say that you are a data analyst and your task is to estimate average weight of adults aged from 20 to 30 living in, let's say, Kuala Lumpur, right? So, well, measuring the weights of every single male within this group, age group, is impractical, right? And there are 100,000 more, right? Lots of. So, how will you do it? So here are some questions. How will you select your sample? How can you ensure your sample is representative? What should be your sample size? So, okay, If you have neighbors, talk to your neighbor for a couple minutes, or if you like, you can pause the video and think about these questions and come back. All right. So basically, to answer these questions, we need to understand sampling distribution, sample mean. We are not going to refer these questions, address these questions in this video, but maybe in upcoming videos we can discuss about these things. But this is like giving us motivation why we need the sampling distribution. Okay. Now here are the learning objectives. Define the concept of sampling distribution. That's what we do, and then we will demonstrate how to create and interpret sampling distribution, and then we do this connection between the central limit theorem that we mentioned earlier. Okay. So what is a sampling distribution? So sampling distribution of the sample mean, it is a probability distribution that describes how sample mean varies from sample to sample. So in other words, I pick a sample and then look at the sample mean, and then I repeat this experiment many times. Let's say that 1,000 times. And then I look at the distribution of all the results that I obtained. So that's what will give me sampling distribution. So what is the purpose? The purpose is, from a small sample, make a prediction, make an inference about the true population mean, right? That would be the ultimate goal. Well, the sample distribution depends on the sample size, so let's be more precise. So first of all, given n positive integer, sample mean xn bar is the average of n data points in a sample selected from a population, right? So the formula would be you pick x1 through xn, add them up, divide by n, that will be the sample mean. Again, what was the purpose of sample mean? So we use sample mean to make prediction about the true population mean. To avoid confusion, let's be careful. So there are three different distributions going around. Let me clarify. So first of all is the population distribution, right? So for example, in our case where we state problem, it's the population distribution, the distribution of weights of all adult males ages from 20 to 30, right? And often we don't know its distribution, right? It could be some weird distribution, it could be skewed, it could be normal, it could be uniform. We have no idea, right? Okay, so that's the population distribution. What is the sample distribution? Sample distribution, for example, you pick 5 adults and just look at distribution of these weights, like 5, there are 5 different weights, you look at the distribution of 5 weights, okay? So as you can see in this picture. So it's, with the fewer points, you have some distribution, right? Okay. Kind of, when n is kind of larger in sample distribution, when n is sort of large, you're getting close to the population distribution, okay? Okay. How about the sampling distribution? Well, again, sampling distribution is what? You pick a sample of, let's say 5, you look at the average, you look at another sample, look at the average, another sample, look at it. So you keep this experiment many times, and then their distribution is what? Sampling distribution, okay? Sampling distribution. So this is, okay, it's not coincidence that I put here bell curve. So here we have a nice looking normal distribution. Okay, now I will demonstrate how to calculate the sample mean. So let's say that I pick 5 adults, and here I have their weights, and I want to calculate the sample mean. Well, it's easy, right? So it's x5. So you add all the weights, divide by 5, so 72.6. So that's one sample mean. Again, for sampling distribution, you would repeat this many times. So here, let's repeat this experiment with another 5 adults, and then again. So keep the averaging. So you keep doing this experiment many times, you take the average, finally you get what you want. So let me demonstrate using this online stat book. So there is a nice way to illustrate. So I will demonstrate using online stat book. So here we see the first one is population distribution, so you can play with it. It could be any distribution because initially we don't know what distribution is. Now what we do is I can animate, right? Let's say I pick 5 random from this distribution. So here 1, 2, 3, 4, 5. And then in the next, in blue, what we see is it calculates their mean and puts here. So if I keep doing this again, another 5 sample, another average, and so forth. So if I keep repeating, slowly we see that this green blocks are building up the our distribution, sampling distribution. Okay, so let's do this like 10,000 times. That's what you get. Let's do it 100,000 times, right? So I can change the distribution here, but I still have the, regardless of what distribution you have, you still have the normal bell curve, right? You still have the bell curve. Well, this is for sample size and 5. What happens if sample 25, right? So let's visualize. So let me do it 100,000 times. So that's what we get. Let's change the distribution again. So that's what we have. So what we see here, notice the mean 1624, 16 roughly the same, and it's close to what we have here, right? So yeah, here if you repeat again, so we see that mean is close to, that's how central limit theorem predicts. But what else? How about the standard deviation? So original is like 5, here it's like 2 point something, here it's even smaller. Anyone wants to point out why when with n increases my standard deviation gets smaller? So standard deviation corresponds to how spread your distribution is, right? So here it's less spread when n is large. So think about it. Okay, so basically from our demonstration from online stats book page, we saw this, right? So we saw that when n is 25, we have sort of distribution is less spread compared to what happens at n equal to 5, right? So what is the reason? Well, the reason is central limit theorem, right? So smaller spread is due to central limit theorem when you have large sample. Because of what? Well, because we know from central limit theorem is that the standard deviation for your sampling distribution will be sigma divided by square root of n, where capital N is the sample size, right? So clearly if n is large, your standard deviation is small. Well, standard deviation is exactly what it says, how spread your distribution is, right? Right, so going back to central limit theorem, what it says in terms of sample distribution, it says the sample distribution of sample mean is roughly normal with mean mu and standard deviation sigma over square root of n. But this is when n is large. What is the rule of thumb? Well, rule of thumb says that if n is bigger than or equal to 30, we can assume that we have the normal distribution. So let's do an example, right? So I have x bar mean of random sample of size 50. So n is equal to 50, right? I have size of 15, and then with population mean 65, so population mean 65, and then standard deviation, so population standard deviation is 5. So now find the mean and standard deviation of x bar. Okay, what do we know from central limit theorem? We know that the mean is equal to mu, so which means mu of x bar, it's exactly mu. In our case, this is 65. Okay. Secondly, how about the standard deviation? Well, what is the, okay, standard deviation, let's look at the variance first. So what is the variance? Well, according to this formula, it's sigma square, right? It's sigma square divided by n. Well, sigma square is 25, n is 50, so that gives me 1 over 2, right? Hence, the sigma of the standard deviation of the sample mean is square root of 1 over 2, which is 0.7071. All right, now let's go to the second one. Find the probability that x bar is less than 64. All right, so mathematically it means this, right? Probability x bar is less than 64. What do we know? We know that my x bar or xn bar is normal, which means I can pretend x bar is normal, but to use the tables, what do I need? I need to convert it to standard normal. What is the process of converting to standard normal? Well, it's x bar minus mu divided by standard deviation is sigma over square root of n. You do the same here, square root of n. All right, then my left hand side, that's my standard normal, that becomes my z, right? That's by CLT. Okay, this is, okay, mu is 65, right? So this is minus 1 divided by my sigma, so this is my sigma over square root of n, right? So this is 0.7071. So that's probability z. If you divide minus 1 by 0.0771, you get minus 1.41. Right, so what do we do next? We read the table, right? So minus 1.4 is here, and the 100th digit is here, 001. So we look at their sort of intersection, hence the answer is 0.0793. So that's the probability that the sample mean is less than 64. Well, if you don't want to read the table, you can also use, again, online statbook.com or other sources where you can also calculate the CDFs. Okay, finally, the homework. So you can try to do this homework. If you find the answers, please write me on the comments, and I can check if it's okay or not. So